Hello everyone, welcome back. This week we do actually have a working computer, and I'll actually be talking about the orbital calculation today. I won't be talking about the math. That is a future side project video that I'll do, um, talking about it. But today I mostly just want to show off the code and kind of some of the features of it. So it's decently long, and this is fundamentally just a fancy orbital calculation plus delta V. Um, so let's just look into some of our settings. So right now, as mentioned in the launch vehicle video, I use the Falcon 9, but in here I have a toggleable Falcon Heavy. I also have a reserve fraction. It was used in previous versions, but now I just have a printout of how much fuel is left on the second stage, because I think that's more important than arbitrarily being like 10% for reserve. We have toggles for using the star kick stage, which is a solid rocket motor, which is quite frequently used for, you know, doing a large burn. But we don't actually use it, but we can easily do it. I have a very basic arrow capture system. It's not amazing, I will not lie. And of course, as mentioned, I have a pork chop search. And that's basically to determine the minimum delta V. So which launch day is the best, and things like that. I have it searching for 600 days. Really doesn't need to do that. I can probably set it to 10 based on what I actually know. And then we have a printout of the top 12. Go anyway where behavior. This is just in the calculation to output wherever the spacecraft ends. So let's say we don't have enough delta V to actually leave Earth. It'll show that we're still in low Earth orbit. Or it'll tell us that we didn't actually make it to Mars. So it's pretty simple. And then plot control. If you're me and you do the iterative design, then you don't really need to see the plots most of the time. You just need the printout. But I'll keep that on there for now. So the most important things I would say are right here. So we have the mass of our spacecraft, and this is when it's wet. So wet basically just means when you have full propellant load, and pressurant, oxidizer, depending on whatever it is. Here we're using monoprop, hydrogen to be specific, so we don't really have to worry about that. We only have to worry about pressurant, and I don't count pressurant as part of the wet mass. Well, it is, but I count it as part of the dry mass, and I count it as unchanging. The reason I do that is just, the amount of feet per second or meters per second that I'll lose from that is just not worth it to do the full calc, and it's better to be on the reserve side. So right now, the third, technically fourth stage of the rocket, I guess third stage, yeah, is just under 7,400 kilograms, and when dry is above 3,500. So that's pretty good. I have a Monarch 1 or Monarch 445 as my main thruster. I only have one. This is a generic kick stage. I believe it's a Star 26 that I base that off of. It doesn't really matter because I don't use it. And then we've got some launch vehicle second stage. So this is to determine our extra gubbins, our mass, and things like that about our second stage to determine how much fuel is left and how much we can actually use. And then important things, mission geometry. What do we want our final things to be about Mars? So, well, I want my altitude to be 250 kilometers. That's what I currently have in the mission timeline. And we currently have a final inclination of 120 degrees. That is for the probes to be re-entried, though I have realized that 90 would also suffice. But I have the delta V to do so. And then, of course, pork chop needs to start on a date, I currently have it in the 2028-2029 launch window, just like the mission. And it starts there, and it really just waits 10 days. So there's some other settings in here, a lot of math. I won't quite go into that because I think that's less interesting. So let's rerun it. It's not the most efficient script. It is in Python, and I didn't exactly optimize it, but it does what I need it to do. So let's just take a look at our printouts. Oh boy. Alright, well, let's start with the graphs. So first of all, this is a bad graph because I currently have a bug in it. And this is not actually in the version on GitHub right now because I'm testing it. Basically, I wanted to show the initial capture orbit. So our final orbit around Mars is rather good. No real qualms. Looks about right to me. And then we've got a delta V breakdown. And this is to basically do our Earth departure. And as you can see, we have plenty of leftover in our second stage. The spacecraft speed, not very interesting. Our true anomaly, not very interesting. Heliocentric distance, not very interesting. Heliocentric view. So as you can see, we are doing a Hohmann transfer. Pretty simple. And a little fanciness. We got some fancy graphics, 3D. Okay, let's dive into the math here. So for our pork chop plot, we can see that the lowest delta V is on the 20th. So that's what the system uses. 'Cause obviously you want the least amount of delta V. And if you want to force a date, you can just set the pork chop scan to 0 and then set your date. So it's not something you have to do all the time. So our total time of flight is 208 days, pretty good. And you can see our departure burn is 3.6 kilometers per second, which is expected. So stage 2 information, so we're using the Falcon 9, and we're saying the capacity to go to low Earth orbit in the non-expended version is 22,000 kilograms. So basically we determined the amount of fuel. These are not official values, but they're values you can find online. And we also we save 11,000 kilograms as reserve, just not used. There's a couple reasons I do that. It's very hard to calculate everything. So I'm determining the sum for getting to low Earth orbit, and then obviously I need to make sure that we can do that burn. So, and I would also like to state for the MAGPIE project itself, this version will be improved. In fact, it has been, but that's a very prototype version right there. So it will be improved, and these numbers will probably get worse in terms of how good they look. And that's mostly just because I want to make it more realistic. This is much farther than a back of the napkin math, but it's definitely not like mission ready math. So as you can see, we end off with about 25% of fuel left. Air capture, it's there, it can be used. We're not using it in this. So basically we're doing our burn 2 after escape, and we only need that much fuel or that much kilometers per second. So we do a nice 15-minute burn, use that much fuel. Or sorry, we use this much fuel. And then we need to circularize at Earth. So we do our burn to leave low Earth orbit, and then we do our burn to capture, and then we basically use up all of our fuel to circularize and get to our right plane. You'll see that we use most of the fuel for that. And yeah, we could do a direct ascent, and that might be worth it. But as a standalone mission, I think it's more important to have more precision. So totally, we do 36 passes because I max out the time to 8 minutes, and that's also a set variable that you can change in this. The shorter it is, the more efficient it is, but the more passes you have to do. At a certain point, it's hard to restart an engine. Hydrogen is pretty easy, and these engines are very much rated for it. But I wanted a large margin of safety, so I said an 8-minute burn. It felt right to me. I can probably go down to a 5, and I might to reduce fuel usage. So our total propellant means that we have 10% left. That's pretty good. And we have a basic calculator in here that determines how much we could actually save. But you may go, hey, that number's bigger than the prop remaining. Well, it's because when you reduce the mass, there's less mass you have to push into orbit and move around, and so it means you need less mass to do so. So if if I were to remove just this mass, I would still have extra mass. I would have less of a percentage difference. Excuse me. But yeah, so that's the orbital calc. Pretty simple. I recommend playing around with it. I plan on some big improvements in realism and the math, but definitely go take a look at it. All right. Thank you very much for watching. Have a great day. Bye-bye.